The next topic in section 13.3 is that of an orthogonal projection. This is a measure of how much of one vector points in the direction of another vector. Now, we already set the stage for this when we talked about computing work. When we were computing work, we had a force vector, and we only wanted the portion of that force vector that was in the same direction as our distance vector. So we will be generalizing that idea in this application. So we can think of an orthogonal projection of u onto v as the vector with its tip at the point where a perpendicular dropped from u to a line v would intersect that line. So, or excuse me, a line that through vector v. So here's u right here, and then you think of having a light up above it, and the projection is it casts a shadow. That vector u casts a shadow, and it's right here. That little shadowy bit, that is the projection of u onto v. V is down here, right, that vector. Technically, it's the line containing that vector, which will make more sense to you on the examples on the next page. But it's the line containing that vector, and that shadow goes from here down to here, and that's the orthogonal projection. So we denote the orthogonal projection with this symbology right here. So let me get that. This is saying the projection of u onto v. It's a new vector. Which is the projection of u onto v, or the line containing v, as it were. The length of the orthogonal projection is called the scalar projection of u in the direction of v, and is denoted as scale v into u. So that would be the length, or excuse me, the magnitude of the projection. So if I say this, the scalar projection. So the scalar projection of u onto v is equal to the magnitude of the projection of u onto v, following the same magnitude definition that we know and love. So that's what that second line is saying. All right, well, this doesn't mean much to us unless we go do a few of these. So let's go practice some examples. Okay. So starting off at the beginning, we have for each set of vectors, draw the projection of u onto v, write the components of the projection of u onto v, and then give the value of the scalar. Okay, so nothing to it, right? Okay, so let's see here. And unfortunately, I forgot to put these into the notes, so you're just going to have to follow along with me here. So v will be right here. So there's v. V is 6, 0. And u, I'm going to make go right here. U is 4, 2. Okay. All right, so the projection would be the shadow that u casts onto v, or the line containing v. So if you think of a light or a flashlight, torch if you're British, up here casting the shadow down, that shadow would come right down here, and so it would be right there. That little vector right there, that is the projection of v, or excuse me, u onto v, which in our case would be 4, 0. No, they will not always be this easy. This one is particularly easy. So I've drawn the picture. Right, there's part 1. I wrote the components. There's part 2, and then I need the scalar of that. So 1 second. So I just want to make a little note. There's part 1, there's part 2. For part 3, I need the scalar. So the scalar of u onto v would be equal to the magnitude of that. So that's the square root of 4 squared plus 0 squared, which we all know is 4. So there we have it. There's part 3. Well, I guess I don't need that part. That'll just confuse you. And there we have it. Okay, now what if I have that same vector v, which is 6, 0. So v equals 6, 0. But what if u goes the other direction? What if u is, sorry, that was a little bent. But what if u is -2, comma 4, like that. All right, so this is where the light kind of thing fails us just a little bit. So you imagine you have your light shadow, your flashlight casting the shadow. But remember, it's not the shadow onto the vector, it's the shadow onto the line containing the vector. And this is why, because if you have your light source up here, orthogonal to your vector v, then your shadow is right here. That is the projection of u onto v. It would be -2, 0. That's why they allow us to have the line, not just the vector itself, because the vector itself, of course, might not be going in the direction we need. All right, so there's part 2 right there with those components. Part 3 is just I need the scalar of that, which should be really easy because it's just going to be the square root of -2 squared plus 0 squared. Oopsie, my -2 got weird there. So that would be 2. Done. So we have our projections and we have our scalars. All right, let's see. What if our vector v is a little short? So what if v is 0, 2? So there's v, which is 0, 2. And what if u is 4, 4? Okay, now what would the projection be? Well, you wouldn't be shining the flashlight from up above. It's an orthogonal projection, orthogonal to the vector. So you'd be casting your light this way, oops, sorry, directly this way, right? Orthogonal to the green vector v. And so your shadow would actually be here. It'd be over 0 up 4. So the projection is drawn right there. There's your projection. Part 1. So part 2, let me just say it. So the projection of u onto v is 0, 4, because it's the line containing the vector v. So that line contains, well, in this case, it's the entire y-axis. And so therefore, that shadow gets cast there. And the scalar for it, again, will be 4. It's the square root of 4 squared, which is 4. Easy as pie. All right, now what if they're both diagonals, just to toy with us? All right, so let me have vector v going at 3, 3. So there's v. V is 3, 3. And then u, I'm going to have be -1, -3. So I have u go like, like that. So u is -1, -3. Okay, well, in this case it'll help if we kind of draw the other side of v. So there's v right there, well, the back half of v, the line containing v. And so my projection is going to go this way. It's going to go from this tip orthogonal into that vector, well, the line containing the vector, right? So it's going to go that way. So my shadow is right here. And then how far was that? Well, I went a little far actually. Sorry about that. So, but it would be in that direction. And you can see it's a little bit past -2, -2, but we're not 100% sure what it is at this point. But we can take a guess. So our guess is that it looks like the projection of u onto v is sort of -2.2 comma -2.2 or something like that. It's just a little bit past 2, 2. And then the scalar for that, and we were just kind of eyeballing this. Obviously that's not going to work in the long run, but for this particular problem it's fine. It would be the square root of each of these squared. So it would be the square root of 2.2 squared plus 2.2 squared. There we go. Which, using a calculator, hold on. Quickly just adding this. Squared. If if you want to see it. Look at that, 2.2 squared, 2.2 squared. So I take the square root of that, and I get about 3.111. So close to pi. I should have aimed for that. All right, so 3.111. Obviously, in the long run, that whole guesstimating thing's not going to work great for us, but you get the general gist of it and how a scalar and a projection work. But we obviously need a nice way that'll be able to work for us algebraically or analytically, if you like. And that is what the next page will do for us. But we'll cover that in the next video.